Hi everyone, we are Team Infinity. Our project aims at using energy and environment-related data to reveal useful trends and relations between these sectors. Our team members are Francis, Christina, Sayan, and myself. Our data comes directly from the United Nations, one of the most comprehensive sources of country-related data. The UN database is vast and contains huge amounts of information that is updated on different schedules. The information is stored in a unique way. Each row of a data set contains not an assortment of numbers, but one single value and the dimensions that that value corresponds to. We'll talk about this in more detail in our pre-processing stage. To give a brief overview of what this means, here's a snapshot of what the data frames in the UN database look like. Note that only the quantity is information, while all other columns simply describe where this quantity belongs. Fortunately, UN provides an easy-to-use API for users who are looking to access large amounts of data through automation. The data provided through this channel is stored in STMX format. Among many things that is true of the STMX standard, it only stores one value per row, and therefore has as many rows as it would have entries if stored in a pandas data frame. This is true to our observation in the Snapchat we showed a minute ago. The advantage to doing this is that, without special structure, the usual pandas data frame row-column format is only readable to humans if there are exactly 2 dimensions. However, this approach is extendable to when we have more dimensions to illustrate. With a complex data structure like energy across different sources, transactions, and nations, this format helps towards the data being stored in a structured way. In addition, this also translates well to MongoDB's BSON format, which stores data in a very similar way. The other important thing about STMX is that instead of storing large descriptive strings as elements, it uses codes to represent each string, and then stores the mapping from codes to strings in a separate file called a code list. Therefore, the data we obtain from the API contains codes instead of meaningful description. During pre-processing, we will need to use the code list provided through the API to transform the data frames back to their readable format. With that, we arrive at our data pre-processing pipeline. First, we pull the data from the UN API. This data contains many rows of codes and values. We then use the code lists to transform each code back to their interpretable counterparts. After that, we parse the data frames into a format accepted by our MongoDB database. It's worth noting that for plotting and modeling purposes, the data will later be transformed from this row format into a 2-dimensional representation. This will be done through some code that lies in our actual application. I'll hand it over to Sayan to describe the actual setup of our app.
Thanks, Ben. So we shall go over the details of the app in subsequent slides. But for this slide, we're going to just do a brief rundown of the web server and what happens under the hood when you visit the website and start interacting with the app. To begin, we obtained a dynamic DNS hostname from noip.com to my router that is then port forwarded to a connected Raspberry Pi. For those who do not know, a Raspberry Pi is a small single board computer with a 1.4 gigahertz quad-core ARM A53 chip and a 512 megabyte DDR2 SDRAM that runs on a Raspbian OS, which is a Debian-based Linux distribution optimized for a Raspberry Pi. Now, since Dash cannot serve more than a single web page, we have a Flask web server that has 2 ancillary pages, the landing page, which also contains the details of our dashboard, and a project description page and the app page, interlinked with each other for easy navigation. The auxiliary pages are pure HTML with CSS obtained from free Bootstrap templates and then rendered by Flask. Now, the app itself, though, is written in Plotly Dash and receives and sends responses to the Flask server, which in turn provides the responses back to the user. The data for our project is fed to Plotly and is obtained from the MongoDB Atlas Cloud Database Service. We unfortunately were unable to host the database locally as some incompatibility between the Raspbian and the PyMongo. Nevertheless, curating the MongoDB CRUD operations properly provide sufficiently quick data fetches with no perceptible lag in service. With the front end and the back end setups now clear, Francis would do a more thorough rundown of the app. Francis.
Hi, this is Francis. I'm gonna walk you guys through the app we made. Our app has 3 website pages: a main page, a project description page, and a dashboard page. And now let's just click into them and take a look. The main page is the first landing page. It contains our project title and team background at the beginning. And if we scroll down the page, we'll see an executive summary, including the intro of our dashboard and also the intro of the time series prediction we made. And also we have the possible next step that we can take to make our website more informative later. And below are some previous works that we drew insights from. And now let's go to the project description first. We firstly introduced our data sets, and then we go to our the whole web development process, which Ben and Sayan have already talked about, and then the data access as well as the database use, and how the database looks like. And at the very bottom, we will add our screencast window later. And now let's go back to the main page and go to the dashboard. The dashboard describes different types of energy data for different transactions for different countries between 1990 and 2017. And it will update itself according to the UN data website. And the first drop-down list here allows us to select the transaction. We have, let's say, primary production, total energy supply, final consumption, and etc. And the second drop-down allows us to select the certain commodity, for example, oil products, electricity, natural gas, and etc. And depending on the selection, this map will display the average distribution over the years for each country. And right now we are at the total energy supply of oil products. And the dark spots here, like for example, China, Turkey, Mexico, and also Mexico's here, yeah, and Brazil, have relative high supply because of the color. And we can see when we hover on the map, we can see the actual amount. And maybe let us maybe switch to the import to see what's going on here. Yeah, and it's very obvious that US has a very decent amount over the past several years, and we can click on the map to even see more details about it. So here we have this quantity of imports of US from the 1990 to the 2017. And there are 2 y-axes here. On the line shows the actual import, and the bars shows the CO2 emission for each year. And from this diagram, we can see a very strong correlation between the import and the CO2 emission. Now I'm gonna hand to Christina to talk about even more detail of our dashboard and our prediction.
Thanks, Francis. Right now we have the year chain of the oil products of inputs in the USA across different years. So if we click on a specific year value, like in 2012, and here is a very detailed breakdowns of the transaction combinations of oil products in the USA. And the right bar chart is a detailed breakdown of different commodity combinations of the imports. If we change the value to, let's say, 2017, the value changed as well. Since I record that values for transformations of oil products, it's 36.3% in 2012, but right now it's 37.6% in 2017. The bar chart also changed accordingly. So what it tells us, when we got to have the breakdown of the transaction combination of certain products and also the energy imports combinations, we can observe how the energy structure changed for a certain country across years. And we know the energy structures has a very close correlations to the climate change. And I think this could have some meaning or shed light to each country, how they could change the energy structures accordingly to help with the climate change. For our enhancement part, we have a predictions based on each transaction, each commodity, and also for each country. For example, here we select the imports and oil products. So based on the previous data, we predict the imports for oil products in USA next year to be 4.5 million. Next, I'll be talking about how this model works. So here we have the data for primary production electricity for USA across from 1919 to 2019. Then for each commodity, each transaction, and each country, we predict the value of the next year's. We use the rich regression model, and here's the results that we have for the primary production of natural gas, for example. We can see most of the country, the axis is the country index, and the right axis has two dimensions. One is the error rate, another is the absolute error value. We can see most of the countries has a very reasonable error range across different countries. But we can still observe that for some country, it has a blue spike. This is because for smaller countries, they have very small absolute value data points. But for large countries, the large countries' values is like hundreds or 1,000 times larger. And that's why sometimes we could see the huge spikes appeared. But overall, we have the absolute error rates at 0.0477, which is not bad for a basic model. So this is our very basic time series predictions. And thanks for watching. This is all for our presentation.